Hello and welcome to the next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In the last class we discussed about the concept of cross validation, which is important to understand the robustness and reliability and the generalizability of a machine learning framework. However, the other important thing that we can do before we go on to study complex machine learning models is that we have to know how to tune hyperparameters. In one of the previous lectures we already learned about model training. We learned about patch gradient descent, stochastic gradient descent, as well as several variants of stochastic gradient descent like ADAM, RMS prop, momentum and so on. However, we have so far not discussed about how hyperparameters involved in machine learning models can be tuned. So today's lecture will be devoted to that, and we will examine how hyperparameter tuning can be done. This will allow us a segue into another tutorial wherein we will show how linear regression models can be tuned and hyperparameters like the regularization factor in lasso and ridge regression can be determined. So let us go ahead and get started. So the topic for today is hyperparameter tuning for ML models, and I want to take a minute to remind you what hyperparameters are, right. We discussed this in one of the early lectures, but it is good to recollect what it means. So hyperparameters are configuration variables, model and training configuration variables that must be specified before model training, since they determine the model architecture and the details of the training procedure. Okay. So they do determine your model architecture, right. So for example, deciding whether it is a linear or a quadratic or a cubic polynomial, you need to do that before the training happens. So it is like a parameter, the degree of the polynomial considered, and similarly things like the learning rate, right, especially when you are using gradient based methods, they have to be decided before the training happens. So that is what is a hyperparameter. So I will now list a few examples, right, which will prove to be instructive before we go on to the act of hyperparameter tuning. So in ridge regression and lasso, the least absolute shrinkage and selection operator that we had introduced several lectures ago, the regularization parameter lambda, right, which determined the penalty on the parameters being too high, right, that is a hyperparameter because it needs to be set before the training happens, right, and in one of the future tutorials we will discuss how this is done. Another example can be determined from the support vector machine models. So in a support vector machine, which we have not yet covered, but we will do so in one of the future lectures. So in a support vector machine shortened as SVM, there is something called a kernel which can be used. So the type of the kernel, which is essentially a function which maps a nonlinear space to a linear space or vice versa. So the kernel type, again the regularization parameter and the kernel coefficient. These are all hyperparameters, they have to be specified before the training starts. Now if you go on to a random forest model, which is essentially a type of a decision tree, and this is again something that we will cover in one of the future lectures. So for a random forest RF model, the hyperparameters can be the number of trees considered, right. So if you look at the word forest, right, why is it called random forest? Because we use a collection of decision trees wherein the features are selected randomly from the available list of features. So that is why it is called a random forest. So the number of trees in this forest is a hyperparameter, the maximum depth of the trees. So how many leaves and nodes are there in the trees, that is a hyperparameter, and the minimum number of samples or data points needed to split a node, right. In a decision tree, the nodes keep on splitting, right, till you reach the final decision node, and the minimum number of samples needed to split a node is again a hyperparameter, right. So hopefully this gives you an idea of the kinds of hyperparameters. Of course you have already encountered ridge regression, whereas things like support vector machine and random forest are new to you, but the hope is that in one of the future lectures you will get to know the intricacies of these models, because they are also very important for our core engineering disciplines. So the last example I want to present, and of course you know that every ML model can have some hyperparameter or the other unless it is just plain linear regression. So for a neural network, right, which is again a very important type of an ML model that has gained a lot of popularity, the kinds of hyperparameters are the learning rate, the batch size, the number of layers in the neural network. So neural network is shortened as NN. So the number of layers in the neural network, the number of nodes in each layer, that is also a hyperparameter, and then the activation function, the function that introduces non-linearity into the neural network, and the type of optimizer used, that is even a hyperparameter in a neural network, because you have to set all of these factors in before the training can proceed, right. So I hope this gives you an idea of what kind of model configuration variables there are and what kind of training configuration variables there are, right. So if you looked at the examples here, this learning rate is a training configuration variable, the batch size is a training configuration variable, and the optimizer is a training configuration variable. On the other hand, things like the number of layers, the number of nodes in each layer, and the activation function, these are model configuration variables, right. So I hope you get a good feel for what are the kinds of hyperparameters that we may have to train for a machine learning model to work most optimally. So now that we have finished our discussion on what are the types of hyperparameters, at least some exemplary cases, we can now move on to discuss what are the ways used to tune the hyperparameters. So the next topic is how are hyperparameters tuned. And we will discuss various things such as grid search, cross validation, randomized search, cross validation, and Bayesian optimization, right. So let us go ahead and understand these concepts. So the first method that I will discuss is called grid search cross validation or grid search CV. That is also the name of the function in scikit-learn that you will have to use. So, in grid search CV what you do is you have a grid of specified combinations of hyperparameters and each of these combinations are used to determine the cross validated model performance. And once all the combinations are used, right, the particular combination which gives rise to the best cross validated performance is chosen as the optimal set of hyperparameters. Okay. Now this is very nice because you have a wide grid and you sort of looking at every possible combination, but the limitation is that this can certainly be computationally expensive. Right, and thus works well for small search spaces. Right. So, essentially what is happening in grid search cross validation is you have to specify a grid of values, right. So, if you look at for example the learning rate if you look at for example the learning rate or the number of layers, the number of nodes, right, you have to give a grid of these and then based on that grid, right, all possible combinations of these will be searched and then the best possible combination will be employed. So, this is certainly computationally expensive, right. So, how it works in practice may look as follows. You consider various sets of hyperparameters, right. So, set 1, set 2 and you let us say try up to set S, and for each of these you tabulate the average cross validated performance, right. So, this is average over say 5 folds. So, you will have the average and let us say using the RMSE. So, average RMSE for set 1, average RMSE for set 2 and so on and so forth up to the average RMSE in set S, and you will then choose the particular combination which gave you the lowest possible RMSE, right. Now, the important thing is once the best set of hyperparameters are determined and let us say it was this set 2 just for example, right. Once the best set of hyperparameters are determined, then you go back and you train the model on the entire training set, right, with the chosen set of hyperparameters, and only then you deploy it on the test set. This is because every data point is valuable, right. When you want to make the final production model, you do not want to lose any data points, right. So therefore once hyperparameter tuning is done, you go back and you train on the whole training set, right, not leaving out any data point. So once the best set of hyperparameters is determined, one retrains the ML model using these hyperparameters and the entire training data. Not leaving out any validation data per se. Subsequently, on this final model, the performance of the unseen or the performance on the unseen test data is evaluated, right. So the sequence is as follows. So first you have hyperparameter tuning, hopefully in conjunction with CV, right. Like I said, there is another alternative to cross validation, that is simply validation. So then you do not change the validation set, you have just one validation set, but that is of course less robust, but it is possible. So you should usually do hyperparameter tuning in conjunction with CV, then you should retrain the ML model with optimal hyperparameters on all the training data. And finally you should test the model with unseen data in the test set. Okay. So this can be your model workflow, and then this test error is reported, right. That is the test error that is usually reported. Okay. So I hope this procedure makes sense to you, and one point that I want to clarify, which I also mentioned while shortly ago, is that note that any type of CV, so we discussed several, right. We discussed k-fold cross validation, leave one out cross validation, or the random subsampling cross validation. So any type of cross validation can be used in principle, although k-fold cross validation is preferred. Right, due to its convenience and robustness. So it is a good compromise. However, for very large data sets like billions of points or at least millions of points, it is possible to use a fixed validation set rather than carrying out CV, right. So, this is done to reduce the computational cost and also because a large data set would imply a representative validation set, right. So, if the data set is so large, if you sample from it to determine the validation set, you have probably sampled all kinds of data points and therefore, you can just work with a fixed validation set, right, rather than doing cross validation. And of course, the most robust way however is to certainly do cross validation, but the choice is left up to you depending on how much computational power you have, right. So, that is k-fold cross validation in conjunction with grid search CV, right. So, now you know how grid search CV can be used to find the optimal model parameters. The next type of hyperparameter tuning technique that I want to discuss is randomized or random search cross validation instead of grid search cross validation, and here we randomly sample hyperparameters or hyperparameter choices and examine their cross validated performance. Right, and the good thing about this is that it is more efficient than grid search, because you are not forced to go through the entire grid of possible hyperparameters, right. So, it is more efficient than grid search CV for a large number of hyperparameters. However, as always there is a flip side, right, to anything. If there is an advantage, there is also a disadvantage, with the disadvantage being that it can miss out optimal hyperparameters sometimes, combinations, since the search is less exhaustive. Okay. Again the choice of the CV that is done, the CV can be k-fold CV, it can be leave one out CV, or it can be Monte Carlo CV and so on and so forth, right. Whatever possibilities existed for cross validation that are even possible here, right. And without CV, like I discussed, usually you only do it right for a large data set. So, this means you are using a fixed validation set. Again it is possible, but right is only when data set is large, right, and large sort of depends on your definition. and also it is preferred when speed is critical. Right. For example, during model prototyping, right, wherein you have various prototypes and you are trying to evaluate the best one, you may want to use it without CV. Okay, so I hope that gives you a good flavor of what is meant by grid search CV and randomized search CV, and these are both available in the model selection module of scikit-learn. The third and the last type of CV that we will consider in this NPTEL course is Bayesian optimization of hyperparameters. Okay. So, here the approach is slightly different. You do not directly work with the cross validated model performance. What you do instead is you try to exploit the Bayesian approach to probability and statistics to create a probabilistic model of the ML models, right, cross validation score, which essentially is an objective function that needs to be optimized. Okay. So, you create a probabilistic model of the machine learning model's CV score, which is an objective function. So, either you may want to maximize the R squared, right, the cross validated R square, or you may want to minimize the cross validated MAE or MSE or so on and so forth, right. So, you create a probabilistic model of this particular objective function, the model's cross validated performance, and then you use this probabilistic model to select the next choice of hyperparameters to evaluate, right, the cross validated performance. Thus, right, it is more efficient than grid or randomized search CV, right, and there are various packages available to do this. There is something called scikit optimize, there is Optuna, and so on and so forth, right. There are obviously other approaches for hyperparameter tuning that we will not consider, right, in this particular course, but you are welcome to read other sources, other books online and understand about these. These are things like successive halving of the hyperparameter search space, evolutionary search, things such as the genetic algorithm employed to optimize hyperparameter, and the gradient based approaches, but those can only be used for continuous hyperparameters, they can't be used for discrete parameters. So these approaches are typically less used than the 3 that we have discussed, right. So I hope this lecture gave you a good idea as to how hyperparameter tuning is done, and this is a key aspect of machine learning. So without hyperparameter tuning, we can't be sure that we have developed the best possible model for the data set at hand. We discussed various approaches, particularly this grid search CV, which goes through an entire grid of hyperparameters. We discussed randomized search CV, which is done for very large hyperparameter search spaces, and we also discussed Bayesian optimization, where a surrogate model is used to optimize the choice of the hyperparameters. I hope you learned something new from this lecture. Thanks a lot for joining in, and I hope you will join the next lecture. Thank you, and I look forward to seeing you then.